Hello everyone, we're going to talk about trigonometric functions of acute angles today, but before we do that, we're going to recall a few things from geometry to make sure we're all on the same page. So I drew a Cartesian plane. This will just be a regular XY axis, right? And I have my origin right there, so that will be the point 0, 0. And on that circle, I am going to draw, I'm going to put a point somewhere on the circumference, and it doesn't really matter where on the circumference I put it. So I'm just going to put it right there in quadrant 1, and I don't know what that x and y value is for that point I just drew, so I'm just going to keep it very generic and say point P is at x, y, because we know that to be correct, right? Whatever x is, whatever y is, that point P is at x, y. Now, I can draw a segment between my point P and the origin, and that is the radius of my circle, and so then I can call my segment I just drew here R for the radius of the circle. Now, all of that being said, I would like to find the distance between the origin and my point P. So I would like to find what R is. And to do that, we're going to do the distance formula. So we have 2 points. We have x and y. That's my point P. And then we have the origin, which is at 0, 0. And the distance formula, if you recall, was x2 minus x1 squared plus y2 minus y1 quantity squared, and that will be equal to the distance between the 2 points. I'm going to call my distance between the 2 points r because it is the radius of the circle after all. And so the distance between point P and point O would be the square root of x minus 0 quantity squared plus y minus 0 quantity squared, and that will be equal to the radius, so the distance between the 2 points. Now, if I simplify underneath my radical and I square both sides, I would end up with x squared plus y squared is equal to r squared. And this is the equation of circle of any circle of radius r centered at the origin. Okay, so we need to know that, and we need to be able to recall it quickly. X squared plus y squared equals r squared will be the equation of a circle centered at the origin with radius r. Now, let's look at how we're going to link this to trigonometry. So I am going to say, okay, I have an x and a y axis. So here's my x-axis, here's my y-axis. And I'm going to draw, it won't be perfect, so forgive me, but I'm going to draw kind of a little piece of a circle here. And that's the origin, 0, 0. Actually, I don't want that big, so I'm going to say this will be the origin, point O, right there. And then I'm going to put a point on the on that circumference of a circle. Now, understand that I didn't finish my circle completely, right? But you can imagine that circle. And then I'm going to just put a point here somewhere on that circumference of the circle. And this is going to, and then I'm going to link the origin to that point on the circumference, and I'm going to go beyond it. So this is a ray. And if I'm thinking about my x-axis, being the initial side of a ray. So that will be my initial side of an angle centered at the origin. And then I'm opening up. So imagine you take that x-axis and you're opening it up counterclockwise. And then the ray I drew will become my terminal side of my angle. And I'm going to call this angle theta. This is an angle, so angle theta is drawn in standard position and what does that mean? So that is the vertex is at the origin and the initial side is the positive x-axis, the positive I say x-axis, but I really should say the positive horizontal axis, right? Because it doesn't have to be x. So the positive horizontal axis. That's an angle drawn in standard position. So you want to remember that. Standard position. All right, where am I going with that now? So what else could I tell you about this? Angle theta, let's change color. So angle theta right there. So this side here, if I drop a perpendicular line to my horizontal axis, I'm creating now a right triangle, right? Because I dropped a perpendicular line from my point that is on the circumference. And then that side of the triangle, that leg, will be, in respect to theta, will be the adjacent side to theta. And then this perpendicular we dropped right there. Oh, I lost it. Is the other leg of the right triangle, and it, in respect to theta, it is across from theta, so we call it the opposite side to theta. And what I called earlier the terminal side is just going to be your hypotenuse for the triangle, right? So that will be your hypotenuse. Okay, so that's a whole bunch of review of vocabulary that we're going to use, and we need to be able to use it fluently. We are knowing what we mean when we say all of those things. My angle theta that I drew is an acute angle, so theta is an acute angle. And what does that mean? That means that it is between 0 degree and 90 degrees if measured in degree. And it is between 0 and pi over 2 if measured in radian. Notice also that when I put the radian notation down, I do not have any symbol to show radian. So when you don't have a symbol with your 0, it is assumed that this will be the radian measurement. And if you measure in degree, you need that symbol for degree to make sure that you show this is measured in degrees. Okay? All right. Okay, let me look at my notes. What else should I tell you about? I think I pretty much have it. All right, so let's look at ratios of sides now. So again, I kind of took that triangle I had up here and I extracted it from my old mess there, right? So this is still a right triangle. This angle here is my acute angle theta. This here will be my side X, the leg X, and this is the leg Y, and this will be the radius, right? Because remember, when we're looking at that here, my terminal side is going to be between the origin and the point on the circumference. Therefore, this would be the radius, right? So I'm going to call it R. So here is just that right triangle reproduced outside of that Cartesian plane, so we can see it better so it's not too messy. We have our adjacent, and remember this is always in respect of that angle theta, adjacent side. We have the opposite side, opposite to angle theta, and then the side opposite to the right angle is always going to be your hypotenuse. All right, and now recall from geometry the trig ratio. So let's put that down, trigonometric ratios. So we have the sine of theta will be opposite over hypotenuse, right? So opposite is my y value, my y side, so y over the hypotenuse, which is r. We have the cosine theta. Hold on, I want to backtrack for a second here because I don't know how much you guys did in that. So let's just say sine will be opposite over hypotenuse. I'm not going to do that too often, right? It's just here for the first time. Which would really be the y over the r, which is what we had. The cosine theta will be the adjacent over the hypotenuse, which is x over r. And then the third trigonometric ratio will be the, I'm writing too many letters here, will be the tangent theta, which is equal to the opposite over the adjacent. Now those are your main trig ratios, and then we have what we call the reciprocal trig ratios. So the reciprocals would be, so reciprocal trig ratios are just like their name indicates, the reciprocal of the main one. So the one that goes with sine will be cosecant of theta, and that will be 1 over the sine of theta, and that will be the hypotenuse over the opposite, which is really just going to be r over y. The reciprocal of the cosine will be the secant of theta, which is going to be 1 over the cosine theta, which is going to be the hypotenuse over the adjacent, and that will be r over x. And then finally the reciprocal of tangent will be the cotangent of theta, which is 1 over tangent theta, which is going to be the adjacent over the opposite, and that will be, oh, I didn't put my tangent there, did I? That will be x over y. And let me add that I noticed that I didn't actually finish that, right? The tangent here should be opposite over adjacent, that should be y over x. Okay, so those are the 6 trig ratios, and notice how those are all abbreviated. And if I don't abbreviate them, then what would it be? Well, what are really those names unabbreviated? Well, the 3 main ones: sine, cosine, and tangent. Those are the 3 main ones. And then the reciprocal of sine is cosecant. Reciprocal of cosine is secant. And reciprocal of tangent is cotangent. Those are the full names of those trig ratios. All right, the next thing we want to pay attention to is those trig ratios really depend on theta and not on the size of the sides of the right triangle. Let me reiterate that, that's important. Those trig ratios really depend on theta. It is a right triangle, right? We're looking at right triangle trigonometry here. So we have a right triangle, and then we have an acute angle, theta. And so those 6 trig ratios really depend on that acute angle theta, not on the side of the legs and the hypotenuse. And to illustrate, I drew 2 similar triangles. So those are 2 right triangles, and they are similar. So they have the 3 angles are equal. So I have my theta right there and theta right there. And then obviously the third angle will be congruent as well, right? Because the angles of a triangle have to add up to 180 degrees or pi. And so when I'm looking at that, and this is not drawn to scale, right? So forgive me, but when I'm looking at that, I'm going to look at my side. Let's say this is 3, 4, 5, which is a Pythagorean triple, right? Then if I want to find the sine, for example, the sine of theta, so sine of theta for this triangle in particular, opposite over hypotenuse, that will be 3 over 5. Okay, so let's keep that in mind. And here we're going to the similar triangle that obviously doesn't have the same length for the side. So we're going to say, for instance, this will be 30 maybe. Remember I said not drawn to scale, 40 and 50. Well, they're similar triangles, so the sine here of theta will be opposite, which is 30, over hypotenuse, which is 50. And when you simplify this gives you 3 over 5, and those two are the same, right? So similar triangle are really showing you that the trig ratios depend on the size or the angle theta, not on the size of the legs and the hypotenuse. All right, where do I go now? If I give you an acute angle theta that is drawn in standard position and passes through the point 2, 3. So we're going to have an acute angle theta. And we use a lot of theta. So how about I change that? So how about we use alpha for a change? So we have an acute angle alpha in standard position. So remember, that means the vertex is on the origin and the initial side is the positive x-axis. And its terminal side passes through, oops, can't spell, sorry about that. The point 2, 3. So we're going to call point P, 2, 3 are the coordinate, the ordered pairs of that point. And our job is to find all 6 trigonometric ratios. Okay, ready? So first we're going to do a sketch. So I already placed an x and a y axis here. And we need the point 2, 3. So I'm just going to kind of sketch it, right? We don't want to count or use a scale or anything. I'm just going to say, let's say this is about the point 2, 3 right there, not to scale. And I'm going to draw a ray or a radius that goes from the origin all the way to my point there. Here we go. I'm going to drop a perpendicular line to my x-axis, and I have a triangle, a right triangle, right? Here, oops. Here is my right angle, and my angle alpha is right there. And that point should be the point 2, 3. Okay, we have everything we need. So if this is true, we already know that the x value here is 2, right? Meaning that short leg here is going to have a length of 2. My y value is 3. That means that the long leg here is going to have a length of 3. And then I still need to figure out what my hypotenuse is here. So I'm going to call that, I don't know, let's call it C. Okay, how am I going to find C? Well, we talked about the Pythagorean theorem earlier, right? This is a right triangle. You have 2 sides, you're missing one. So you're going to use the Pythagorean theorem. You're going to say a squared plus b squared equals c squared. So we're going to have, using the Pythagorean theorem, and that will be a squared plus b squared equals c squared. We're going to solve for c. So we're going to have 4, right? That's 2 squared plus 9 is equal to c squared. And now I don't want c squared, I want just c, right? So 4 plus 9 is 13. Take a square root on both sides. And c is equal to the square root of 13. Okay, so I have what C is here. So now we have the 3 sides of the triangle. We can find the 6 trigonometric ratios. So we're going to start sine of alpha. And remember, the sine will be the opposite side of the angle. So opposite will be 3. So it will be 3 over the hypotenuse, which is square root of 13. Now, if you recall from geometry, we can't leave the radical in the denominator. So we're going to have to rationalize that denominator. So that's done by multiplying by a square root of 13. And by the way, why is that true? Why can we do that? Because this is just a fancy one, right? Anything above itself just simplifies to a 1, and when I multiply anything by 1, I really haven't changed anything, right? It's still going to be the same. It's just going to look different now, which is what I wanted because I wanted to lose my radical in the denominator. So this is going to give me, let's go back to green. It's going to give me 3 square root of 13 over 13. Okay, so that's your sine. Then I want the cosine of alpha. And the cosine is going to be your adjacent over the hypotenuse. And again, we need to rationalize that denominator. So we're going to multiply top and bottom by the square root of 13, which is going to give me 2 square root of 13 over 13. Okay, that's the cosine. Now I need the tangent of alpha. Tangent is opposite over adjacent, so that will be 3 over 2. And no need to do anything here. Those are my 3 main ones. So let's change color and let's go to our reciprocal ones. So the reciprocal of sine is cosecant. So cosecant of alpha. And now you can do several things. I would always go back to my very original one there and just take that and do the reciprocal. And so that will become the square root of 13 over 3. Really, when you're looking at the triangle, it will be the hypotenuse over the opposite, right? So square root of 13 over 3. And there is no radical in the denominator, so we're good to go. The second is the reciprocal of cosine, secant alpha. And same thing, I'm going to look at, instead of doing 2 over square root of 13, I'm going to have the hypotenuse, square root of 13 over 2, and that is good to go. And then the reciprocal of tangent is my cotangent alpha, and that will be not opposite over adjacent, but this time adjacent over opposite. Okay, here are the 6 trig ratios of this angle alpha going through the point 2, 3. All right, so now let's do a little bit of a proof. So what are we trying to show now? Okay, let's write what we're doing here. So we're going to say an equation involving trigonometric functions of an angle and let's call this angle theta again. That is true for all values of theta. So that is true for all values of theta is a trigonometric identity, and I'm going to put that in a different color, is a trigonometric identity. Now, you've already dealt with identities in your earlier math years, right? For instance, let's put a little bubble here. If you look at two and 1/2, those are multiplicative inverse, and when you multiply them, you get a 1. This will be always true no matter what that number is. 2 could be anything. So really, a times 1 over a is always going to be 1. This is an identity. The Pythagorean theorem is an identity. So a squared plus b squared is equal to c squared for any right triangle A, B, C. This will be a true equation, a true statement. So that will be also an identity, etc. So any of those that would involve an equation to be true for any input that you're going to replace a variable with, and in our case here it will be theta. Okay, so let's explore this a little bit further. So we're going to say sine theta, so let's explore. So we know sine theta will be equal to y over r, right? Remember we started with that, right? Where are we? Sine of theta, right there, sine of theta, opposite of hypotenuse, so y over r, right? So this is always true. It's no matter what theta is, that's an identity. And then we have the cosine of theta, we know always to be x over r. Now let's put those two together. And let's say, well, what would sine of theta divided by cosine of theta be then? Well, it will be y over r divided by x over r. And when you're simplifying that, they're both over r, that would simplify to just y over x. But then if you're looking at y over x, and if you recall what we said up here, y over x is what? It's your tangent. So this is going to be equal to tangent of theta. And that is an identity. So we're going to say, therefore, let's put that in color. Therefore, sine of any angle theta divided by cosine of any angle theta is always going to be equal to the tangent theta. That's a trigonometric identity. Meaning it is always true no matter what theta is. Now I'm going to let you do the same thing for the reciprocal of that. So, and you guys can do that on your own, right? So what happens if you have cosine theta divided by sine theta, right? What would that be? Okay, and you can just explore and figure that out on your own. Now, there is a very famous identity that we're going to use over and over, and it is related to our famous Pythagorean theorem, and it is called the Pythagorean identity. Okay, before we go there, we need to talk something about notation. When we square trig ratios, trig functions, if I need to square sine of theta, for example, I am not going to write it like that, because that would imply I'm squaring theta, the angle value only. That's not what we're doing. So to write that properly, to show what we mean, that we're actually squaring the trig ratio, the sine, we're going to write it this way. Sine squared, and then you put your angle in there. Okay, so that's how you write it. If you needed to put that in your calculator, you would have to write it as such. Sine theta in parentheses and then square on the outside. Okay, so that's calculator notation right there. Okay. All right, so back to the identity. The famous Pythagorean identity is sine squared theta plus cosine squared theta is equal to 1. We're going to need to know this one by heart. Why? How? Why is that true? Well, let's look. So let's do a little triangle. We don't need to make it too big. Here is my right angle, and I want theta there. And we're going to have x for one leg, y for the other leg, and then r for the hypotenuse. And we already know that sine theta is opposite, so the y, over the hypotenuse. We also know that cosine theta is the adjacent, so the x, over the hypotenuse, so the r. And we are going to rewrite that. So I'm going to rewrite this equation by isolating the y. Ready? So I want y by itself, so I'm going to multiply both sides by r. That will give me r times sine theta is equal to y. And now I'm going to do the same right here with the cosine. Multiply both sides by r to get x by itself. So that will be r times cosine theta is equal to x. Okay, now we're going to use all of that. And the Pythagorean theorem here would tell me that x squared plus y squared is equal to r squared, right? So let's translate that here. So the Pythagorean theorem would tell me x squared plus y squared equals r squared. But what is x squared? Well, x squared is just that, right? So x squared is r times cosine theta squared. And what is y squared? Well, y squared is r times sine, so r times sine theta squared, and that would be equal to r squared, right? That's just from above, from the Pythagorean theorem. So you see how I replace the x squared by r cosine theta and the y squared by r sine theta quantity squared. And now we're going to, well, just do a little bit of algebra. So r times cosine squared is just going to be r squared times cosine squared theta, and remember your notation. And then r sine theta quantity squared will be r squared times sine theta squared. And that's equal to my r squared still. And now I'm looking at that, and I have an r squared here and an r squared here, so I can factor it out. So r squared, factor it out, leaves me with cosine squared theta plus sine squared theta. And now all we have to do is divide both sides by r squared. And we have, this is a plus here, right? So addition is commutative, so we can rewrite that so it really looks like my identity right here, right? So it's in the same order. So rewrite that will give me sine squared theta plus cosine squared theta, and r squared divided by r squared is 1. And this, ladies and gentlemen, is how we end up with that Pythagorean identity that we're going to use over and over again in trigonometry. All right. We're at 40 minutes. Let's see what else I wanted to tell you. Maybe one more little thing before I hang up here. If I have a triangle given to me, a right triangle, of course, and let's call this alpha again, so we don't always just think it has to be theta. this is a right triangle, and let's say this leg is 3, this leg is 4, but this one I do not know. So I'm going to call it y, because that will be my y value, right, of that point up here. And I am told, so given cosine of alpha is equal to 3/4. And we have to find all 6 trig ratios. For theta. Well, if I know the cosine is 3/4, the cosine is really going to be adjacent over hypotenuse. And by the way, I did my picture too early because normally this is all you will be given right there, right? And you have to do the sketch yourself. So adjacent is right there. And then the hypotenuse, right? So that will be my 3/4. And then from there, I need to figure out y. Well, at this point, you should be able to see that you're going to use the Pythagorean theorem. So you're going to do 3 squared plus y squared is equal to 4 squared. And therefore, y is equal to the square root of 16 minus 9. And that will be the square root of 7. So y is equal to the square root of 7. And now that we have that, then we can go ahead and write the 6 trig ratios, right? And I'm going to let you finish that on your own. Okay? All right. I'll talk to you in class.